Okay, so let's continue. I really just want to get past 4 and jump into partial derivatives. So we do something a little bit new, but it doesn't matter if you have a constraint or not. Observations, this is number 4, observations. Optimization with interval constraints. It just means with or without a domain. How many domains? You can have 2, you can have 1, you can have 6. I mean, you're not going to have 6 or anything, but there is no number. The previous to this, the previous video number 3, just means we don't have any constraints added. Optimization with interval constraints just means that we have domains that we have set to this thing here. Yeah, so it's always the same. It's always going to be maximizing, no minimizing. But how do we maximize? Take the derivative, set it equal to 0, solve for x. And then we haven't talked about it yet, but what do we have in calculus 1? Define it so perfectly is not important. Understand the simplicity behind math and calculus is. Define it perfect as we do in calc 1 is not important. But anyways, what do we have in calculus 1? We have the critical points. In calculus 1, we have the critical points. What happens if you take the derivative, set it equal to 0, those are check marks, and solve for x? That should just ring in our head. For even if we don't know what we're doing, take the derivative, set it equal to 0, solve for x. Should just ring in our head. But when you solve for x, what have you found? I mean, in these easy problems, you've automatically found the maximum. If you have a crazy, crazy hard problem, which you're not going to get in this class anyways, uh, all you found is a critical point. So we're only making kind of a very simple observation. Whenever you have interval constraints, those are also critical points. So take the derivative, set it equal to 0, solve for x. Hopefully we get something in our, if you get one that's outside of your domain, you can't use it, right? You also have to check your x values with the domain of the function and with the domain of your constrictions. It's very silly, but if we just understand the nature of basic graphs, this is all very easy. Who knows in Calc 1, but once we get to this point of reviewing it, it should be kind of a duh. But what are the critical points? In fact, let's just do this because if we do the problem, it's a lot easier. So it's always the same. Take the derivative. First of all, that's negative 2x. Incredibly, they give us a straight line here. Plus 4, y equals mx plus b. Yeah. Take the derivative, which is negative 2. So we do get this. Yeah. Quite silly. Set it equal to 0, solve for x. Of course, we know a straight line has a constant slope, which is why there's no x. Y equals mx plus b. You take the derivative, all you find is the constant slope. And you cannot set it equal to 0 and solve for x because there's no place where the slope equals 0. So if you get something that can't be set equal to 0, or you set it equal to 0 and you get a statement that doesn't make sense, it means that we don't say undefined, but it means that we have something that doesn't exist or something that's wrong there. Okay, so if we get values there, they're critical points. So that's it. The derivative in this case means nothing. Yeah, x equals 0 and x equals 5. Those are our critical points. You can do a number line and all that and test your critical points. You have more than plugging in. We don't care about that. All we do is we take our critical points and we plug them into the original. Yeah. What do we get there? I get positive 4, negative 2 times 3 equals negative 6. So obviously the 0 will yield that. We have a max because it's a straight line. So negative slope. So I drew it wrong. We don't have to graph. I'm just saying, yeah. So if we have some sort of an interval, yeah, the straight line, the maximum is just going to be at the corner of that interval. We have a max of 4 when x equals 0. Yeah. So we can move on instantaneously. Okay, so the partial derivatives for a lot of us is a new subject matter. They're easy. They're just like calculus 1, single variable calculus derivatives. These are multivariable calculus derivatives. They're very easy. but it'll take at least a couple of videos to describe them. So we'll kind of briefly describe the partial derivative. Partial derivatives, find the partial derivative of each of the following functions with respect to x and y. I don't think, conceptually, we have to understand this very well. This is an xy graph. It's the kind of subject matter where if we keep it simple, we can talk about it for a couple of minutes, and you can take the same concept always and drag it on for like 2 pages, which we won't do, but we try and teach a basic concept that goes into other ones. But in calculus 3, you take the xy graph and you lie it on its side. This is one typical picture such that this shaded area is quadrant 1. It's kind of more of a nice grid there. And then up here is the third dimension. It's going to be the z-axis. So we just drew a 3-dimensional axis. And if you do like a point, it's like a region R. This shaded thing is like what they call a region R in calculus 3, a 2-dimensional plane right there. Yes. But if you have an x value and you have a y value, here's an x, and you try to make lines parallel to the y. Here's a y, you try and make little marks parallel to the x. So just, make kind of a little thing here, parallel to the y-axis, make a little thing parallel to the x-axis. They meet right there. Okay, so if you plug into a multivariable function, this goes up and it equals some sort of a z. Yeah, so f of x is going to be z equals 2x plus 4y. It doesn't matter what you call everything. It's much more common to say y equals f of x1 comma x2 equals 2x1 plus 4x2. I don't know if those look like the same thing, but they're the exact same thing. This is in calculus 3, we use z, but in a lot of applications, you just say y equals f, and all the inputs are x1, x2. So that's a graph. So I'm kind of getting to a point here. That's a basic 3-dimensional graph. I don't want to make every point in the world. I just have to define the 3-dimensional graph really quick before we go on. So I'm just making up a function, it's like one of these. If we had calculus 3, it's one of these, not conic sections, but like a 3-dimensional conic section. We don't have to review the hyperbole, whatever they call these things. We don't care. I'm trying to talk about the slope. Okay, so this video is going to come to an end. We're going to do all of this in another video. We're going to do partial derivatives. I'm just kind of trying to show the basic thing. When you take a derivative, you're finding a function for the slope. You're finding an equation for the slope. If you take a partial derivative, you can only take, there's 2 partial derivatives. There's the partial of f with respect to x. They use funky d for partial derivative. And that means you're taking the derivative with respect to x. So if there's 2 variables, there's always 2. If there's 3 variables, x, y, and 3, z, which there could be, there's always 3. What is the second derivative? It's the partial of f with respect to y. But what we're saying, in a way, what is the whole point of everything I'm doing? There are 2 slopes. Yeah, let's just limit it to 2, x and y, which will basically be it for this class. If you take the derivative with respect to x, you can only take the derivative with respect to one thing. If you take the derivative with respect to x, what you did is you found the slope along, that's the y, sorry about that. Yeah, you find the slope, yes, you find the slope parallel to the x-axis. If you do the y, you find the slope, yeah, parallel to the y-axis.